Hey everyone, and welcome. Today, we're going to decode the secret language that's running behind the scenes of your social media feed, your online shopping recommendations, and even the GPS in your car. We're talking about graph theory. And trust me, it's a simple but incredibly powerful way of seeing all the connections that shape our modern world.
So let me ask you something. Have you ever stopped to wonder how your phone can sift through millions of possible routes and find the absolute fastest one? Like, almost instantly? I mean, how does it do that? The answer is actually really elegant.
It thinks in graphs. That's the secret. Your phone turns the entire road network into a massive graph so it can figure out the best path. This is the core idea. And once this clicks, I promise you're going to start seeing graphs absolutely everywhere.
All right, so where do we even begin? Well, we've got to start with the absolute basics, the language of networks, the fundamental blueprint. Okay, so at its very core, a graph is super simple. It's just made up of two things: nodes, which you can think of as objects or points, and edges, which are just the lines that connect them. The easiest analogy? Think of a map. The cities are your nodes, and the roads connecting them are the edges. Simple as that.
Now, when we talk about how big a graph is, we use two little letters, N for the number of nodes and M for the number of edges. So if you look at the example here on the screen, you can see we have N equals 5 nodes and M equals 7 edges. Okay, so once you have a graph, you can start moving around in it. A path is basically just a route from one node to another, and its length is just how many edges you cross. Now, a cycle is a special kind of path. It's one that starts and ends at the exact same node. Think of it like a round trip. So check this out on the screen. See that path from node 1 all the way to node 5? It crosses 3 edges, right? So we say its length is 3. And that other highlighted bit, that's a cycle. You go from 1 to 3 to 4 and right back to where you started at 1, forming a nice closed loop. Now, what if you can get from any node to any other node in the graph? We call that a connected graph. But sometimes, a graph might be broken up into these separate islands of nodes that aren't connected to each other. Each one of those islands is called a component. Okay, now that we've got the basic blueprint down, let's start adding some cool features to make these graphs a little more like the real world. You see, edges aren't always a two-way street. Sometimes they're undirected, which is like a normal road. But other times they're directed, like a one-way street with an arrow. The perfect example is social media. When you follow someone, that's a directed edge. It points from you to them, but it doesn't mean they automatically follow you back. All right, let's go back to our GPS for a sec. We know not all roads are the same, right? Some are faster, some are shorter. That's where a weighted graph comes in. Each edge gets a number, a weight, that could represent distance or travel time or even the cost of a plane ticket. Now, the goal isn't just to find any path. It's to find the path with the smallest total weight. Okay, so we've described graphs. Now let's get into the really interesting part, analyzing them and uncovering some of the fundamental rules and properties that they all follow. Okay, pen and paper time, because this is a big one. You will definitely see this in an exam. A node's degree is just the number of edges touching it. Now, here's the magic trick. If you add up the degrees of every single node, the total will always be 2 times m, the number of edges. Why? Well, think about it. Every single edge connects 2 nodes, so each edge adds 1 to the degree of 2 different nodes. It has to add up. All right, time for a little brain teaser. Look at this graph. Could you color every single node using just 2 colors, say red and blue, with one rule: no 2 connected nodes can have the same color? Go on, give it a try in your head. The answer is actually pretty deep. So, a graph that you can two-color like that has a special name. It's called bipartite. And here is the absolute golden nugget for your exams. Write this down. A graph is bipartite if and only if it has 0 cycles of an odd length. A single triangle, for instance, has a length of 3. That's an odd number, and that's a deal breaker. And this slide right here shows you exactly why that rule works. See that triangle? That's a cycle of length 3, an odd number. Let's try to color it. If you make the top node blue, then the other 2 nodes it's connected to must be red. But wait, those 2 red nodes are connected to each other. You can't have that. See? It's impossible. That one little odd cycle messes up the whole thing. So we can draw these graphs and understand them visually, but how does a computer actually see them? How do we turn these pictures into data that a program can actually work with?
Well, there are basically three main ways to store a graph in code. You've got your adjacency list, your adjacency matrix, and your edge list. Picking the right one for your problem is super important for making your code run fast, so let's quickly break down the pros and cons of each.
This table really lays it all out. Honestly, for most cases, you're probably going to use an adjacency list. It's fantastic when you need to quickly find all the neighbors of a node. Now, the adjacency matrix, its big advantage is that checking if an edge exists between two nodes is instantaneous. But man, it can eat up a ton of memory. And the edge list, it's the simplest of the bunch, perfect for when you just need to loop through every single edge one by one.
Okay, deep breath. Let's pull all of this together. Think of this as your exam quick-fire review section. If you're prepping for a test or a technical interview, you are going to want to pay very close attention for the next couple of minutes. This is your cheat sheet.
First up, the vocabulary. You need to know these cold: node and edge, path and cycle, connected and component, a tree, and bipartite. If any of those are still a little fuzzy, just hit rewind for a quick refresher.
Next, the key rules. Burn these in your brain. The sum of degrees is always 2 times the number of edges. A tree with n nodes has exactly n-1 edges. And of course, bipartite graphs have absolutely no odd length cycles.
And finally, let's talk about the traps people fall into. These are the common mistakes you really want to avoid. First, when you're coding an undirected graph, please remember to add the edge in both directions in your adjacency list. Second, don't use that memory-hogging adjacency matrix for a huge graph with very few connections. And last, don't mix up path length, which is just counting the edges, with the total path weight in a weighted graph. They are two different things.
And there you have it. You now have the fundamental blueprint of graph theory. It's like having a new lens to see the hidden connections all around us. The rules themselves are pretty simple, right? But what you can do with them in logistics, social networks, biology, it's literally limitless. So the only real question left is, what problem are you going to solve first?